we will discuss the geometric significance of vector products a bit more, and then we'll dive into what we call a mixed product. So we've previously pointed out that if you take the magnitude of the vector product, it represents the area of the parallelogram. So keep in mind you need the magnitude of that. Well, by definition, geometric definition, if I cut this parallelogram in half, it will give me the area of the triangle that those two vectors form. So in general, you can take half of that, will give you the triangle. So these two are nice facts that we can use to solve different questions. So let's try it with this one. I have triangles with vertices A, B, and C, and they're setting it up nicely, but in case they don't give you this part A where you set it up, you have to immediately realize that, okay, before I even start finding the area of the triangle ABC, I need to actually find the vectors that they form. So it doesn't matter in which order you take them. It might not even be in this correct order, but you can have a look at it at any direction. So remember that these are points, but I need the area of the triangle that they form, so I need the actual vertices they form. So let's call them U and V, or as the question stated, we can label this as AB and AC. And it won't matter which direction and so on, because eventually we'll be taking the magnitude of the vectors of the cross product. So to find A and B, remember that you need to take vector B first and take away vector A, and that will give you -3, -4, and 1. And then vector A to C, I'll just skip writing the numbers. It will result in this. Now that I have these two, then to solve part B, the vector product used to find the area of the triangle is going to be half of the magnitude of the cross product. So I need to take AB times AC. And you need to, again, be careful that you set up everything nicely, times -2, -2, and 2. Now, remember that vector products are not commutative, so if you do AC times AB, it will give you the same digits, but negated to this. However, in here it won't really matter because we're taking the magnitude, so the order does not matter. If the order mattered, then they would have told you, and it won't be a question related to area or so. But the fact that we're taking magnitude will not have an impact. So going into, I'll do my quick method of hiding each component that I need and then doing the multiplication. Again, do take your time to do the multiplication, making sure you're not messing up the negatives and so on. So if I want the I component, I need to take -4 times 2 minus a 1 times -2, which will give me a -6. If I want the J component, I start from the bottom here, 1 times -2 minus a -3 times 2, and that will give me a 4. And then for the last one, the K component, it's a -3 times a -2, and then minus a -4 times a -2. So many negatives in there, so just be careful, and it should give you a -2. Now the magnitude of this is, don't forget how to find the magnitude. You are taking the square of each value, so it's 36 plus 16 plus 4, and you're gonna have half root 56, which is 3.74 units squared, or units, you can write it as squared. So that's the area of the triangle ABC. Now we move on to something called a mixed product. Now there's no reference to mixed product in the guide, but performing successive calculations, for example, find the vector product and then do the scalar, that shouldn't be unusual, and it is a useful skill to have. The formulas given, unfortunately, are not in your data booklet, but you can easily calculate them by taking them step by step. So when we combine vector and scalar product, we can do, we get the following. So you have a vector here, and then this is a new vector that you have, and you're taking the scalar product with another vector. So the final result is actually going to be a scalar value. Keep that in mind. There are some facts here. So if I take A times B scalar product of C, it will be the same as doing B product C and scalar A. Notice how you have to follow the same direction. So A, B, C, A, B, C. So A, B, C, A. And then again, A, B, C, A. So C, A, B. So basically you're following a pattern of A followed by B, followed by C, followed by A, followed by B, followed by C, and so on. And then it will be the same as going the other way, but obviously negated here. Now there is a formula in case you have vectors A, B, and C. Here, if you have vectors A, B, and C, and you are meant to find the scalar vector product of them, to find the vector product, you can do it manually. First find the vector product of A and B, and then do the scalar product of C, which is something I prefer, to be honest. But there is a formula that you can use. It's a bit long, it's not in the data booklet, but you can write it down and reference through it. So for example, so if you want A times B with a scalar product of C in this order, you have about 6 terms that you have to calculate, and then you simplify them all together. The first 3 are positive, the next 3 are negative. You can do it with a pattern if you want to, but that's just extra unnecessary memorization. That's why I would avoid using a formula unless you always have it in front of you. So it starts with A1, A2, A3, and then a minus A1, minus A2, minus A3. This is easy. But then you need to memorize how the B values go. It starts B2, B3, B1, B3, B1, B2. And then for the C, it starts C3, C1, C2, C2, C3, C1. So a bit, C is a bit weird to remember. But if you can remember this, you can use it immediately to find the value here for the mixed product. I will tend to use the long route just to show you that it works. Then the formula could be used if you want to, just to check that the answers are the same. So let's talk more about geometric representation. We talked about the area, we talked about triangles and so on. Well, if I take the mixed product this time, and what will happen is if I have 3 non-coplanar, so they're not on the same plane, 3 non-coplanar vectors, they can create a parallelogram prism, so a 3D parallelogram, or as it's called, a parallelepiped, or a parallelepiped, different pronunciations. Now, the volume of this is basically just the volume of the base times the perpendicular height. Now, notice that C is not the perpendicular height, H is the perpendicular height. So we'll talk about how to find that. Now, the base area is basically just the area of the parallelogram. Well, we know how to find the area of a parallelogram with vectors. That's just basically the magnitude of the cross product. So I know the first part of the volume of this pyramid. Now, how do we find the height? Well, the height is basically this H value. I need to find it. Well, let's go back to basics in geometry, and that is taking a right angle triangle here. And let's represent this as theta, as the angle between A times B and C. So theta will be between A times B and C. Now, if I want to find the length of H here, I know that C is my hypotenuse. I have the angle. I'm looking for the adjacent. So the cos theta is equal to the adjacent over the hypotenuse. And then, so this is a vector here. And then I will cross multiply, so the height is just c times cos theta. So the perpendicular height can be found through c times cos theta, where theta is the angle between those two. So combining all of this, I have the magnitude of a times c and magnitude of c cos theta. Well, keep in mind that this is not an unusual formula. We've seen this before. If you have the scalar product of two values, an alternative way is to take the magnitude, and the alternative way to calculate the scalar product is to take the magnitude of each multiplied by cos theta. So basically this is what's happening here. You're taking the magnitude of one vector and then a magnitude of another vector and cos theta. So basically you're taking, this is another way of saying, well, I'm taking the scalar product of these two. So it's the scalar product of this vector and that vector. So what we've showed is that the mixed product, the magnitude of the mixed product is basically the volume of this prism, a parallelepiped. And we obviously take the absolute value. The definition does not depend on the order of vectors. So if you need to, because of the absolute value, so if you need to calculate the volume, you don't need to be concerned about which order to do the A, B, and C in. So let's try a few examples. And here I need the volume of the parallelepiped enclosed by these three values. Again, no need to worry about the order. I'll go the long route where I'm actually going to take the cross product of A and B and then take the scalar product with C, keeping all the calculations in order. So A times B will be negative 1, 1, minus 2, and 2, 1, minus 3. Now I'm going to skip the long explanation of cross product, so we should know how to do that. It's 1, minus 2, and 1. Then I'm going to take the scalar product with C. So that's 1, minus 2, 1. And the scalar product with C will be 1, minus 2, 1. And this will just give me a 10. And then if I need, the last step is just to make sure that you take the absolute value of that, because you're doing the volume. So the absolute value of 10 is just 10. You can put the absolute value here from the beginning. You could have done that. So the absolute value, not to confuse it with 1101. So let's just make this thicker. So it's just 10 units cubed, or cubed in there. So because we're doing a volume. Show that question and you should be able to realize what we're meant to be doing here. So if I have three vectors, they're telling you they're coplanar. So how can you prove they're coplanar? Coplanar means they lie on the same plane. So back to the definition of coplanar, it means that I can draw them on a flat surface, all on the same plane. So if they're all on the same plane, it means you have no depth to the shape that you're creating from these three vectors, which means that you have a volume of 0. So remember that the mixed product, if they're non-coplanar, they create a prism, which means that if they are coplanar, they do not create a prism, or the prism will have a volume of 0, which means we're trying to show that A times B, or A cross product B with a scalar product of C, it will give you a 0. That's what we're trying to show. So let's start with that. We'll go for A times B first, and that will be 1 minus 2 minus 4, 1 and 3, sorry, and 1, and that will give me a 2, 3 minus 1. And then I'll start taking the magnitude or the absolute value with the scalar product, and times c, which is 2 minus 1, 1. And that will give me 4 minus 3 minus 1, which is basically just 0. So I have shown that the volume is 0, so volume is 0 is 0, therefore they are coplanar. If only two were coplanar, you can imagine what the volume is going to be, but the idea is that they have to be non-coplanar for the volume to exist. Now, just as we did with the beginning with the area of a triangle, we can also talk about a triangular prism. So if I'm not thinking of the parallelogram that's formed by two vectors a and b, I'm thinking of the triangle formed, and the creating a 3D version of this triangle. So we have a triangular pyramid, so a pyramid with a triangle base and triangle faces. Well, going back to geometry and the volume of a triangular pyramid, it's a third times the base times the height. Well, we know what the base is. The base is just half. So this is the base. The base is just half of the vector product of a and b. And then the height, similar to the proof that I did previously, is just c times the cos theta. And we know that a combination of this gives you the a times b, or a cross product b with the scalar of c, and then the scalars outside will give you 1/6. So this is the formula for the triangular prism. Do not confuse it with the area of a triangle or in 2D. So we're looking at the volume of a triangular prism. It's a sixth times the mixed product of a times b scalar product c. So let's try it with this example. And again, because we're taking the magnitude, the order does not matter. So I'm just going to do a rough sketch, which again might not be accurate. But let's say A, B, C, and then and then you have point D here. So in order to find the volume, the triangular pyramid that's formed by these, I need to actually find the vectors that are formed by them. So this is like the A, B, and C from the previous slide. So you first need to find these values. So remember, you're moving from vertices to vectors. So don't think that these are your vectors. They're not your vectors. They would have mentioned. They're not even written in vector form. So keep that in mind. You need to find A to B, which is you taking B, subtracting A. That will give you 1, 1, and 1. I'm gonna skip the calculations for the rest and just give you the answer. A to C will give you -4, -1, and 2. And then A to D will give you -1, -6, and 6. So then I like to take the long route. I'll do AB times AC with the scalar product of AD. Remember that this is what you're trying to calculate, a sixth of that. So let's just do AB with the cross product of AC. I'll just give the final answer. That's going to be 3 minus 6 and 3. And then taking it with AC and the absolute value of that, it will give you 51, or just 51. So then the volume is just going to be a sixth times 51, which is 8.5 units cubed. So you're just taking the 3 minus 6 and 3 with the, sorry, this should be AD. with the -1, -6, and 6. So just to point out what we did here, -1, -6, and 6, and you're taking the absolute value of that. So hopefully this was clear. You can use the long formula that I showed a few slides ago for finding the mixed product, but I also like to show you that it works and you don't need to memorize any formula for the volume. So this is the geometric significance. Make sure you understand them quite clearly because they show up randomly with questions for vector product and scalar product and the mixed product. Another name for mixed product as well is a triple scalar sometimes, so there are different names used online.